So we'll start with the GUNN diode. Okay, GUNN diode, it is also called as transferred electron devices. Now, what is the reason for this that we are going to see, and how to make use of such kind of diodes in amplification, okay, or for the oscillation purpose. So generally, GUNN diode is used for as an oscillator. Okay, so GUNN diode basically it comprises of N type of material only. Okay, there is nothing like P type. What negative differential resistance, and that's why it can be used as what low power oscillator to generate microwave signals. Now here you can see that this graph it represents field strength versus drift velocity in a sample of N type of gallium arsenide. So this experiment was performed by the GUNN, and the result, which is that result is shown here. So here you can see that as the potential applied to N type of gallium arsenide sample, if it increases, so of course the field intensity through that sample is going to increase. So initially it is observed that as the field effect increases, the field strength increases, then the drift velocity of the electron that increases. So that increase in the velocity will lead to what increase in the current. Okay. Now, after certain voltage, that is what around 3 kilovolt per centimeter. Okay, somewhere here, it was observed that the velocity of the electron, if there is further increase in the field intensity, then it reduces and it settles to a particular value. Now, earlier this reason was not known, but later on some theory was developed to answer this question, why in up to a particular field strength the velocity of the charge increases, but after that it reduces. Because if you look at this particular region where the velocity increases with the applied field intensity, so that region can be called as what, ohmic region. Okay, but if the velocity decreases with the increase in the field, means the voltage increases but the current decreases, that kind of thing is happening. So it means that the device it exhibit negative resistance, and if the negative resistance is existing, then already we have theory that negative resistance can be used for amplification purpose. Okay, or for the oscillation also, sustained oscillation. So the analysis of this region was really important. Now we'll see why this is happening actually. And okay, other thing which was achieved by the GUNN, that he applied a pulse of certain voltage, okay, across that sample. So that pulse was sufficient to provide a field strength from 2 kilovolt to 4 kilovolt across that gallium arsenide sample. Okay, so but the applied pulse was a smooth pulse. Okay, so such kind of fluctuation was not there, but the collected pulse, it contains this oscillation. Now the magnified form of this oscillation is shown here. This is the expanded view. Now since oscillation is there, so it must have some frequency of oscillation. So the time period of this was mentioned, and it was concluded that the time period of this and the time period, that is the transit time of the electron through that sample, it was same. Okay, so it means that by changing the size of the sample, this time period can be changed. So now to answer those questions, why that oscillations are there, or why the velocity of the charge reduces, two value theory and three value theory was proposed. So here there is a list of semiconductor material which are having this certain details, like band gap energy between the conduction band and the valence band. For germanium it is 0.8, For gallium arsenide, it's 1.43. It is larger. Okay, so of course there will be less leakage if you are using gallium arsenide material for making a diode. Then separation between the two valleys. So here you can see that the gallium arsenide, it contains only 0.1 volt, 18 electron volt separation between the two valleys. So if suppose the temperature increases, then at room temperature, it may happen that the electron from lower valley may jump to the upper valley. Okay. So in order to avoid that, we should select a material which is what having larger this energy gap between the two valleys. So gallium arsenide is okay. Then indium phosphide is the another material. So here you can see that there are two different energy levels. So because there are three valleys, concept is there. So that's why the two separate energy levels are mentioned here. Okay. Now the threshold field this threshold field, it represents how much this potential difference you should apply across a sample of 1 centimeter, so that there will be jump of the electron from the lower to the upper valley. Okay, so that voltage. Then velocity, what velocity the electron can achieve. Okay, so there is a peak velocity here, you can see 2.2 into 10 raised to 7 centimeter per second. So for indium phosphate, it is larger. Now the two valley theory. Why now we'll try to answer why this is happening. Okay. So here this is the valence band, you can see. Okay. Then this is the conduction band. There is a separation between the two bands, and that separation is what 1.43 electron volt, which is good enough. Now the conduction band is what divided in number of different energy bands, you can say. So here the electron can occupy this lower valley where the energy is lesser, of course. And here, if the electron gains larger, more energy, then it is said to be what it is shifted in the upper valley. Now let us see the property of the electron in this valley. So if the electron is occupying this valley, then the mobility of the electron here is more, as you can see, it is 8,000 centimeter square per volt per second. And the mobility of the electron is this is the mass, not mobility. Mobility is 8,000, okay? And the mass, effective mass of the electron is 0.068, okay? So effective mass means what? It is not the actual mass, but it is the mass when the electron mass is what measured in the presence of the other electrons, okay? It's not the individual one. When there are multiple charges are there, then at that time, if you are measuring it, then what is the mass of that electron, okay? But in the upper valley, you can see that the mobility, it has dropped from 8,000 to 180 centimeter square per volt per second. And the mass has got increased. Earlier, it was here in lower valley, the mass of the electron is very less. And that's why it can move with a faster velocity. But in the upper valley, the mass increases, so it cannot move with a good rate, okay? And there is a what energy gap from bottom to bottom between the two valleys is what 0.36 electron volt. Now the operation why this velocity of the electron decreases with the increase in the applied electric field intensity, and similarly, and the electric field versus the current, that also has got what similar graph. Means if you are increasing the field intensity, then initially it is observed that the current increases, but after threshold voltage, the current reduces. Now, whether you talk about this graph, that is field versus drift velocity, or the field versus current density, then can be answered with the help of this three graphs here. Here it is what energy. This is the lower valley where you can see that the electrons, because it is N type of gallium arsenide semiconductor material. So the electrons, they are occupying what lower valley, where the mobility of the electron is high, effective mass is less. So if you are applying a voltage which is what less than than the lower value. Okay. So what happens that under the influence of this applied electric field, which is what lesser than the this energy electric field of the lower value. So all the electrons, it will remain in the same value, and if you increase the this electric field, then the velocity of those electron is going to increase because they're in the lower valley, and in this valley the mobility is high. Okay, mass is lesser, so of course the velocity will be more because of the larger mobility. But now you are coming across a situation where the electric field intensity is what larger than the EL, that is what electric field which can supply energy, which is larger than the energy level in the lower valley but lesser than the energy level in the upper valley. So what happens that since the energy is what larger than the lower valley, so some of the electron may jump into the upper valley. Now when it is said that it is jumping into the upper valley, it doesn't mean that the electron has jumped from this cup to this cup. So it is just the graphical representation. Okay. Now why it can jump from this to this? See, it doesn't, as I said, that it is not a cup actually. Okay, so where the electron will be jumping to this height and then additional this height and then will come here. Okay, so here just look at this. The lower valley, the upper valley, it has the minimum energy of this much, and the upper valley will have the maximum energy of this much. Now this level and this level, they are same. So if the applied electric field, it gives a sufficient amount of energy to the electrons which are present in the lower valley. So the electron will be raised to this level, and if it has reached to this level, then this level of the energy and this level of the energy, they are same. So you can say that now the electron, it is present in the upper valley but occupying the lowest level of energy. And physically you can consider that, let us consider that you are representing electron. Okay, so now your behavior will change depending on the applied electric field. So currently you're sitting somewhere. Okay, so you have got certain mass. Okay, but because of the supplied energy, now what is going to happen that let us consider that your mass has got increased suddenly. Okay, so you can see that your position has not got changed, but your physical property has got changed. So same thing happens to the electron. So it is nothing like it is jumping from one point to the other point or one place to the other place, but at the change in the characteristic at the same place of the electron. Okay, so the moment we say that now the energy has got increased, so it means that now the electron, its mass increases. Now the mass has got increased, so the velocity will be what lesser. Okay, and if suppose the electric field is so large that the energy given by the electron, it is very large as compared to the energy of the upper valley. So definitely all the electrons will be shifted to the upper valley. Now there is no further additional valley where the electron can jump. Okay, so all are going to occupy the upper valley. Now in the first case, since all the electrons, they were occupying the lower valley, that's why if you increase the electric field in such a way that the energy level is what lesser than the energy level of the upper valley, so all the electron will be having, because they're having good mobility. So if you apply, if you increase the electric field, then the velocity of the electron will increase. And since the electrons can move with the faster velocity, then the delivery of the charge will be more, and which represents what larger amount of current. And but if suppose the energy has become what larger than the energy level of the lower valley, so some of the electrons you can see it is here. So these electrons will move with the lower velocity, and the electrons here will be what moving with the higher velocity. That is okay. But now the amount of this charge which will be delivered at the other end, that has got reduced. So there will be what reduction in what the amount of charge. And if this is the scenario, so you can see that the entire charges or the particles, they have moved to the upper valley. So even if the voltage increased, then but the mobility has got reduced, so there won't be that much delivery of the charge. So current will be what lesser. Okay, because the velocity has got reduced. So reduction in the velocity will lead to what reduction in the amount of current. And this particular property is used to make what? Negative resistance device, where the applied field is what? Larger, but if it increases, but the current decreases. Okay. Now, with the help of this specific property of the GUNN, this gallium arsenide material, now this particular behavior is used for uh, making use of this gallium arsenide as what? Oscillator. Okay, or in the design of oscillator, you can say. So let's see how the things are going to happen. Now this is a sample of the gallium arsenide of particular length, because length matters. Okay. Now there are two distinct modes in which this gallium arsenide material. Now, since see here there is nothing like P or N type of layer, only N type of sample of certain length. Okay. So that's why there is no concept like what electrodes, two electrodes, positive and negative, that is anode and cathode. It's nothing like that. So that's why the name is what? This bulk, this diode, bulk device. And since the electron is what? Just now we discussed that there are two different values, and the electrons, they are jumping from the lower value to the upper value if they are getting sufficient amount of energy. Okay, that's so that is another reason why it has got different name. That is transferred electron devices. Okay, so electrons, they are transferred to the other value, upper energy level. That's why the name is what? Transferred electron devices. Or sometimes it is also called as what? Hot electron devices, because the energy level of the electrons in the upper value is what? Very high. Now, so I said that the GUNN, this sample of the gallium arsenide material, is used in such a way that it can be used for oscillation purpose. Now there are two distinct modes under which it works as an oscillator. So one is called as GUNN mode or transit time mode. Okay. Now the name is what? Transit time mode. So that is what directly related with the behavior of this gallium arsenide material here. And the second, this mode is what? Limited space charge mode. Okay. Limited space accumulation. So that is called as LSA mode. And all are, these two modes are what? Concerned with what? This particles only. So let us see why the name is what? Transit mode, or that which is also called as GUNN mode. Now transit time mode means what? Here the electrons, they are going to take certain time. Once they are shifted to the upper valley, see, we are going to make use of this sample in the negative range only. Okay, in the negative range means what? We are this region only, where the electric field is what? Larger than the threshold voltage and lesser than this valley voltage here. So because here this region, you can see that if the electric field is more, but the means electric field is increasing, but the current decreases. Okay, so this region represents what? Negative resistance region. So this is the region where we are using this gallium arsenide, N type of gallium arsenide sample, because we are going to make use of it as an oscillator. Now, how to make use of this as an oscillator? So for that, let us try to understand that you are having one tank circuitry. Okay, now this tank circuitry, it oscillates at certain frequency. Okay, that depends on the value of L and C. We are knowing that it is 1 by 2 pi, okay, root of LC, right? So this is the frequency at which this is going to operate. So of course, it has got, if the frequency is there, so I can say there will be what? One fixed time period. There is nothing but 1 by F. Okay. The meaning of this is what? This cycle, period of this cycle, right? Now we are going to discuss about the GUNN mode, okay, or the transit time mode. So this is the sample. As I said that there is nothing like cathode or anode, but now this is what? Your cathode here, and this is your anode, and you have applied. It is forward bias, you can say. Now there is nothing like biasing, forward bias or reverse bias, because it's N type of material only. But here the higher potential is applied, here the lower potential is applied. Okay, negative and positive. Now there is what created in this sample. Defect means what here at the cathode side. There is what doping is not uniform, because of which what here excess amount of this electrons are available as compared to the other region. Or this defect may arise because of the noise the moment you are switching, turning on the system. So because of that transient effect, the electrons which are going to get gather here, that will be more. Now the applied potential, what will be the reason? Either it is created, or it is just because of the noise this has got created, or because of the doping. But here this electron is present, okay, excess electron is present as compared to the other region. Now if you apply a potential difference here, okay, so what happened that because here the charges are more, the conductivity in this region will be more, and because of which the electric field in this region will be lesser, and in the region which is right to this A region, there the electric field intensity will be more. And suppose you have biased or applied potential in such a way that the electric field is what above threshold voltage. So what is going to happen? Now because the electric field here is what lesser, so electron, they are in the lower value, and because of which the velocity of the electron in this left region is what more, but in the upper region all the electrons, they have shifted to the upper value because of the higher electric field. So electrons on the right hand side, they will be moving with the lesser velocity, and the electron on the left hand side, they will be what moving with the faster velocity. So what is going to happen? The electron which are coming from the left side, they are going to enter into the higher this valley. They will jump to the upper valley, and their velocity will drop. So you can say that now here on the right hand side, the slow moving crowd is there, and from the left hand side, a highly a crowd which is what moving with the faster velocity is coming. So definitely these two crowds, they will be merged, right? And a huge crowd will be formed. Now what is happening, since on the left hand side there is what continuously growth in what the number of electrons, and those electrons what they are coming from the right hand side, which are moving with the lesser velocity. So what is going to happen that this kind of distribution of the charge is going to take place. Here you can see that the more, now negative means what, more number of electron, and here positive means what, the number of electrons are lesser in the right hand region. So what is happening, that a dipole kind of situation has come. So the electric field between these poles will be what, very large, okay, and because you are applying a fixed voltage, so of course the electric field cannot be very high, means it has to obey what, conservation law. So what will happen if the electric field is very high, very large between the two poles? So in other region, the electric field settles to a fixed value, which is what, lesser. So now if suppose just impose this graph here, so electric field in this region is very high, but in the left hand region and the right hand region, that is low. So what is happening? The meaning of this is what, the velocity of all the electrons, they are having what, good mobility here. Here also good mobility. So the number of electrons which are entering here and the number of electrons which are leaving here, that gets balanced. So there won't be any further increase in the size of this bunching. Okay. Now you can treat this entire thing as what, a pulse. Like you have created a pulse. Okay. This pulse is nothing but this bunch of electron which is what, moving towards the cathode. And now on the other hand side, you are having what, this circuitry. Okay. So if this pulse is given to a tuned circuitry, so, and this tuned circuitry is what, it is oscillating at this frequency f. Okay, so what is, it is tuned to this frequency, suppose. So the moment this pulse drops here, so what is going to happen, that oscillation will start. But of course this is going to be a damped oscillation. So what will happen, that the magnitude of that oscillation will start decreasing. But what happens, the moment this cycle is over, then the next similar bunch will be delivered to this tank circuitry, and this will keep repeating. So what will happen, that you will get a sustained oscillation, and that is what is shown here. And now why the name is what, transit time mode, because here this oscillation is what happening at natural frequency of the or the occurrence of this formation of this dipole domain. So bunching is formed on the left hand side, that crowd of electron it moves towards the right hand side, and then finally that bunch of the electron is going to collapse by delivering a pulse to this tank circuitry. So there will be what continuous supply of this bunch of electron, okay, and that bunch of electron is going to take certain time to move from left to the right, and that time is nothing but the transit time, and that time is exactly equals to the period of oscillation, okay. So this mode is also called as what? GUNN mode, because this behavior was first noticed by the GUNN, okay. Now the same this concept is used for what? Different modes of oscillation. Here, the frequency depends on the transit time period, but it may happen that you want to operate your oscillator at smaller frequency or larger frequency. Then what is going to happen? So that's why there are two other modes. One is called as delayed mode, and another is called as quench mode. Okay. So in case of delayed mode, you can see that now this is the period, okay, to this vertical dashed line. This is the period for that the electron cloud to travel the sample of the gallium arsenide material, okay. But whereas the oscillation period, you can see, of the tank circuitry is what? Now larger, okay. So you are applying a biasing potential to the gallium arsenide sample, which is connected to a tank circuitry, which is tuned to a lower frequency. Now the moment you are turning on the system, so what will happen? That oscillator, it will start oscillating. So it will generate its own AC field, and the biasing potential will generate its own field. So during positive half cycle, you can see that the AC component and DC component, they are going to provide a sufficient amount of potential difference across the sample, and that potential difference is large enough, or the electric field because of that potential is large. It is, you can see, it is very, very large as compared to the threshold voltage. So what is going to happen? That the crowd of the electron will be generated, okay, like we have discussed here. This dipole that is going to uh, take place. Formation of that dipole is going to take place, and that dipole is what? Moving towards the right hand side, means towards the this tank circuitry, or you can say this anode side, okay. Now the moment it reaches to this is the time when that dipole should reach, okay. So the moment it reaches, so by that time the cycle has become what? Negative, right? So now you can see that the negative cycle and the applied potential, it has what? Gone down to this threshold electric field, and because of which that cloud of electron, it has delivered to the tank circuitry, but the potential across the sample, it is now below the threshold voltage, because of which you can see that next this dipole formation is not going to take place, or the bunching of the electron is not going to take place, because the electric field throughout the sample is what? Less than this ETH. So that will get formed only if the applied potential and the oscillation, these two, gives a electric field which is what? Larger than the threshold voltage. So the bunching will get, or the dipole will start forming at this particular point. Here you can see that the applied potential, because of which the electric field is what? Equals to the threshold electric field. Now from here onwards, that bunching will get formed. It will not get formed exactly at this. That was happening in the earlier case. That's why it is called as what? Delayed mode, delayed domain mode.
Shastri sir, you are not audible. Shastri sir, you are not audible. Shastri sir got disconnected, so he will join shortly.
Mode. So oscillation period is what? Very small as compared to the transit time. So you can see that during the positive half cycle, the domain is formed. It tries to travel towards the anode, but before it reaches to the anode, this is the time at which it will reach to the anode. Before it reaches somewhere here, sorry here, the potential across the sample, it is so low that the electric field created across the sample will be what? Lesser than the threshold electric field, and because of which the domain it collapses. Okay, and now the next time it will start building at this point. Okay, so you can see that here the domain it never reaches. It is getting formed, but it never reaches to the anode. In other two cases, it was reaching to the anode. Okay, because it collapses before it reaches to the anode, and that's why the name is what? Quench domain mode. Next is limited space charge accumulation, LSA mode. So here, actually, domains never ever exist. But you can see that. See what is the arrangement here? That your LC circuitry it is tuned to a very high frequency. So high frequency, now you can see that this is the transit time period from here to here. Transit time period means the time taken by the domain to reach to the anode from cathode end. Okay, there is this much, but the period of oscillation is, you can say, it is very small as compared to the transit time. So what happens that now even if the during from here to here this cycle, the electric field intensity throughout the sample is above this threshold voltage, but the time given for the electrons to form that domain, that is not sufficient. Okay, so what happens that even though the high potential is there, the electrons they are moving to the, you can say, the upper valley, but before they move, they are what? Collapsing. Okay, and the domain formation is not going to take place because the time allowed for the formation of domain that is very less. Okay, so what happens there, since the electric field applied is what? It is in this region, negative region only, but the domain it never forms. So if the domain is not getting formed, so there will be nothing like transit time mode or quench mode or delayed mode. Okay, that kind of thing is not happening because the domain itself is not getting formed. But the electric field applied is what? In this region where the current is lesser even though the electric field is larger. So it means that this diode is simply acting as a what? Negative resistance device. And the role of now this negative resistance device is what? See, this LC circuitry, these are what we say that these are lossless. Okay, so once this LC circuitry which is connected to a supply, if it is turned on, then the oscillation is going to take place. But unfortunately, the oscillation will die very soon. Why? Because there is loss in C and loss in L and in the other part of the circuitry. So if you are able to manage or compensate those losses, then you will get a sustained oscillation. So those compensation is done with the help of what? This GUNN diode, which is what? Negative in nature, negative resistance. So if you calculate the power dissipated, so it will be minus I square into R. R is what? Negative. That's why minus sign is coming. So when I square R is what? Dissipation of the power. So minus I square R with what? Generation of the power. So it takes the energy from the DC source and it will compensate the losses. So in that way it is treated. So here, since the formation of this domain is not there, that's why this is not coming under the transit time mode or the GUNN mode. Okay. Now next is what? Avalanche transit time devices. So here this is going to be another category of the device where we are having diode and they exhibit negative resistance. let us see the concept. The process of having a delay between voltage and current. Okay, so like in earlier case, voltage increases but the current reduces. Okay, so here also delay between voltage and current in avalanche together with the transit time through the material is said to be what? Negative resistance. The device that helps to make a diode exhibit this property are called as avalanche transit time devices. Okay, so first device is what? IMPATT diode. Okay, so here you can see that the IMPATT diode comprises of NPIP region. So N plus is there, means it is heavily doped N type of material, then moderately doped P type of material, an intrinsic semiconductor material, then heavily doped P type of material. And you can see that it is reverse biased. Because of the reverse bias, this N plus P region, okay, that junction is what under reverse bias condition. And this AC voltage, it is not the actual AC voltage applied here, but there is a voltage because of the noise which is coming here. Okay, now because of this doping profile, this is the field distribution, electric field distribution. So you can see that the electric field is very high at the junction here because of the doping. Okay, large doping and doping difference. And in intrinsic region, it is going to be very smooth because here there is no charge is existing. So this is called as what? Space charge region. And since the electric field is uniform, or air is also called as what? Drift region. Under the influence of this electric field, if any charge is coming, that will move. So under the impression of the field, if the charge moves, we call this as what? Drift velocity of the electron. So that region is called as what? Drift region also, or space charge region. Here there is no charge in this region. Now this is the noise, which is actually, see, noise means it should have random potential, not random variation of voltage and this time period also. But since we are making use of this as what? Oscillator, so of course it will have a fixed frequency and with smooth waveform. So out of multiple frequencies of the noise, one particular frequency is chosen. Okay, because here it's not the complete circuitry, but if you are going to make a tank circuitry or whatever is required for the oscillation of certain frequencies, then out of those, one frequency which we want to exist, okay, or we want to collect as output, so that is there. So this applied reverse bias potential and this noise in the positive half cycle, both are in, means they are getting added. So because of which, what is going to happen? The reverse potential which is going to exist or which is going to act between this N plus and P region, that is large enough to cause the breakdown. And because of which you can see that exactly at this peak, the breakdown, it starts. And because of the breakdown, we are knowing that there will be what? Increase in the free electrons and hole particles. Okay, so hole will be moving on the right hand side and the electron will be moving on the left hand side. So this this pulse, it represents what? Increase in the this amount of charge because of the breakdown. So if that charge increases, of course the current is going to increase. And this square box, it represents the average current because of this this pulse of the current which is generated because of the breakdown. Now those holes, I said that they are going to move on the right hand side. So motion of hole is nothing but what? The motion of electron towards the left hand side, because the holes are moving on the right hand side. But you can see that the holes, see, the current because of this breakdown will be set only if the carriers which are generated because of this breakdown, if they are capable to reach in the external circuitry, then only we are saying that the current is set. But in order for the hole to reach to the other end, it has to go through this intrinsic region. Okay, so of course this width of this intrinsic region is what? Length of the intrinsic region is L. So the holes, they are going to take larger time. The electrons here, immediately it will go into the circuitry, it will try to set a current. But before, now those electrons, they are going to be going to move in this entire sample only if these holes, they are going to reach to this point. So if the holes are moving here, then the electrons entering from here, they will start moving and current will be set. But it will, this process will get delayed. Okay, so here now by the time this holes, they are reaching to the anode side, this cycle, it reverses and it reaches to what? Suppose this peak value. And that time a pulse is considered to be what? to exist in the external circuitry. So you can see that the process of this charge building, it occurred at this positive peak, and a current is set in the negative region, where you can see that now the voltage, AC voltage has got increased, but sorry, it has got decreased and the current has got increased. So this behavior is what is going to set a negative resistance. That's why the name here is given what? The process of having a delay between voltage and current in avalanche together with the transit time through the material is said to be what? Negative resistance. Because of this behavior, that here the current is increasing and the voltage is decreasing. Okay, so a negative resistance behavior is found in this IMPATT diode. So IMP means impact, A avalanche, transit time. Transit time, why? Because whatever charges are created because of the avalanche effect, they are delayed. Okay, so they are going to take certain time to reach to the external circuitry. So that's why, and that time taken depends on the length. That's why the name is what? Transit time. Okay, and the same concept is for the TRAPATT here. Okay, same, but here the less number of layers are there, P plus N, and then N plus is there. So here also this junction is operated under reverse bias, and you can see that the length of this N region is larger. So the breakdown is going to take place, and because of the breakdown, whatever charges are created, they are delayed here. Okay, when they are reaching to the right hand side, and the similar kind of behavior is formed, like when the voltage decreases, current increases. Okay, so similar kind of thing is going to take place. Now, what is the difference between the IMPATT and TRAPATT? The TRAPATT it has got higher noise figure. Higher noise figure means what? It is less noisy as compared to the IMPATT. Okay, that is the advantage of the TRAPATT. So TRAPATT is better as compared to the IMPATT because it is less noisy. Otherwise, the behavior is what? Similar. Okay, now how to make use of this negative resistance devices as an amplifier? So negative resistance behavior is there, so you can use it as an oscillator or an amplifier. So here it's a circulator. Already we have discussed circulator is a device in which it's a multi-port device, but the flow of energy or the flow of power, you can say, it is always in one particular direction. It will be never in the reverse direction. So now the signal which you want to amplify, it is applied here, and here I have taken, it's a tunnel diode, because tunnel diode, it exhibits negative resistance. So you can connect actually any device which has got negative resistance. So it can be GUNN diode or your IMPATT, TRAPATT, any. So you can see that the negative resistance is shown here. Okay, so because of that negative resistance, now the reflection coefficient, have a look at this. So negative resistance, and this is the reference impedance of this port. So what is going to happen, that the reflection coefficient will be larger than 1, means whatever AC signal you are transmitting here, more than that will get reflected back and it will be collected here at this port. Since what you are feeding, you are getting more than that, we say that the amplification has been achieved. Okay. Now, the measurement part. So already we have you all have given presentation on this. So it is just the revision of that part, you can say. So here